Hello, everybody. Welcome to today's session in algebraic and complex geometry. My name is Lucia Caporaso. I will chair this afternoon session. It is my pleasure to introduce Aravind Asok from University of Southern California. The title of his talk is Vector Bundles on Algebraic Varieties.
Well, I guess it's my job then to introduce my co-speaker, Jean Fasel. And Jean will actually begin the talk.
Exactly. As a revenge, I will start the talk. So thank you very much for the organization, for allowing us to be here in front of actual people in an actual room. That's very, very nice. Thank you very much. So the title of the talk is on the board. So it's about vector bundles on algebraic varieties. So we were lucky because this morning we had a talk already on vector bundles. So we don't have really to introduce what that is, but we'll still spend a few minutes on that. And then we will introduce our main working tool, which is the Motivic homotopy theory. We'll have some applications, and in the end, we will justify our presence here because we'll speak about complex geometry also. So yeah. Okay, so as I said this morning, we had a talk on vector bundles, but I want to go back to the initial thing in the topic. So we fix a ring R, and we speak about projective modules, which are, as we know from the Swan-Serre correspondence, the analog of vector bundles over topological spaces, right? So usually people are interested in projective modules just because they provide nice resolutions, but we are interested in projective modules because they are interesting to study and because they have rich structural results. So what is a classification? What we do is just we introduce the set of isomorphism classes of projective modules, or vector bundles, if you want. And we also introduce this stabilization map, which is just saying that, okay, if P is a projective module, we just add a free factor of rank R, and we'll get a well-defined map, obviously. So those sets are pointed. We have a free module at each step. So the free module of rank N on the left, and the free module of rank R plus N on the right. And obviously, there is no reason to stop at rings. We can also study the same for any scheme, and we will do it, right? So there is a notion that we also want to introduce because it will make convenient our classification results. It's the notion of co-rank. And well, we will see that this notion is just a very convenient way to measure complexity of results. So the co-rank is just the dimension minus the rank. Right. So the general idea or general question of the topic is just, can we just characterize this map? Can we understand the image and the fibers? So by here, the fibers, so that there is no structure on either set, right? So they are just pointed. So there is no reason to talk about kernels and so on, but you could pick a guy on the right and ask first if it comes from the left and how many preimages you have. So that's the fibers, right? The first example, so obviously the situation depends on N and R, but the first example is just if you take a line bundle, you just add a free factor for anything, and then you take the determinant, then you don't do anything, right? So this map psi1R is injective, which says that the fibers are either empty, if you take a guy on the right, which is saying the composable, there is no preimage, and if there is a preimage, there is a unique one given by the determinant. So from the very beginning, you have nice results, which are actually about the stabilization map. So the first one was obtained by Serre at the very beginning of the theory, saying that, okay, if the ring is of cool dimension D, and here it's an approximation because the real theorem says about something about the maximal spectrum of R, but the approximation is that we take a Noetherian ring of cool dimension D, and if N is larger than or equal to D, then anything on the right is in the image of something on the left. So we say that they split three factors of rank R here. that if you put R equal to 1, it's a free factor of rank 1. Yeah, and then you can ask, okay, we know the image in that case, what about the fibers? There is a few years later, there is a theorem of Bass, which says, okay, if n is large enough, so here large enough is just the dimension of R plus 1, then this map is always injective. So the fibers are always trivial, so reduced to one thing, 1 point. Just to point out the notion of corank, so this is a operative of negative corank, so operative modules of negative corank. So we could say, okay, let's go from negative to say corank 0. That's the next slide. So the thing is that if you want to go to corank 0, you already have to make some extra assumptions. So for this slide, we will take K to be algebraically closed. And well, so in that case, Suslin gave a result. So he proved that this map is actually injective well, so you have to start from the dimension of the ring instead of the dimension plus 1. So it's an improvement on Bass results. And there's a second improvement which was obtained with Ravi Rao and Richard Swan, saying that if you go still one less, so from D to D minus 1, then, well, the map is not quite injective, we don't know, but at least it has trivial fiber. By this I mean that if you take the free thing of rank D plus R minus 1, then its preimage is just the free thing of rank D minus 1. Right, so this is about the fibers of the stabilization map, but you have also a very nice theorem on the image of it. So again, if you start with a smooth affine K-bar variety, which is the same as saying that we take a smooth K-bar algebra of dimension D, then, well, so if you look at the stabilization map from Xi D to Xi D plus 1, then, yeah, Xi D minus 1 to Xi D, sorry. So it's in the image if and only if the top Chan class vanishes. And this top Chan class is an element in the Chow ring, so the Chow ring of codimension D cycles, so dimension 0 cycles, just points, right? So this was proved originally for smooth film varieties. And recently it was just proved by Amayanu Krishna that it's also true if you just assume that it's reduced. But then, of course, you have to slightly modify the definition of the Chow group, but still the result is exactly the same. The statement is the same. Yeah. So now we want to pass from 0 corank to like positive corank, and this is the purpose of this talk.
So in the classical theory of vector bundles, one really useful organizing tool is the Pointryagin-Steenrod theorem, which tells you that topological vector bundles can be identified with homotopy classes. And one of the motivations in the classical theory of projective modules was the analogy between projective modules and vector bundles on topological spaces. And many of the theorems that were formulated there are natural analogs of theorems that were initially formulated in topology. So what we'd like to do is take ideas of homotopy theory and take this dictionary between projective modules and vector bundles very, very seriously and ask if there are sort of analogous classification results in algebraic geometry using the techniques of homotopy theory. So what kind of homotopy theory are we going to do? Well, we use the Morel-Voevodsky homotopy theory. People have very strong opinions now about whether you should invert the affine line or not, but we're going to choose to do so. So this is a theory where one starts with the category of smooth varieties. One extends it in order to perform various homotopical constructions. So there later we'll very quickly see that there are various things that we want to do, which will involve leaving the category of smooth varieties. For example, something like the Grassmannian, an infinite Grassmannian is sort of naturally an object which is not a smooth algebraic variety, but something we'd like to consider. So we enlarge the category of smooth varieties to a suitable category of spaces. I'm going to be a little bit agnostic about what that category is. But then what we want to do is invert some things. So in particular, what we'd like to do is invert the affine line or invert the projection from the affine line. So slightly more precisely, the A1 homotopy category H of K is constructed as some localization of the category of smooth varieties. And just to give you a sense of what it does, well, it in particular inverts this projection from X cross A1 to X. There is a natural monoidal structure here, which is the smash product. That suggests that we're going to be using pointed varieties. And maybe the fundamental difference between classical topology and the situation here is that there are two analogs of the circle. If you take the affine line and you remove the origin and you point it by 1, then that's what we call GM. And there's another circle S1, which plays the role of the usual circle in topology. So these two things have sort of very different flavor, and it's going to be important to distinguish them. So maybe the most important example of the kind of map that becomes an isomorphism in the Motivic homotopy category from our point of view is the following one. If you have a torsor under a vector bundle, then something, or more generally something that's Zariski locally trivial with fibers that are affine spaces, then that's going to become an isomorphism in the Motivic homotopy category. And so maybe this lemma tells you one of the key differences between passing to the Motivic homotopy category and working beforehand. But if you have any smooth variety over a field, then you can always find a torsor under a vector bundle with the total space affine in the absolute sense. So I've attributed this to Joannou and Thomason. In the quasi-projective case, this is due to Joannou. And in the projective case, it's actually pretty easy to give a proof of this. If you think of the projectivization of a vector space and you look at P of V cross P of V dual, and you remove the complement of the incidence hyperplane and you project onto any one of the factors, then that's a torsor under a vector bundle, in fact, the tangent bundle. And it's easy to see that the fibers are affine spaces. And well, once you've done it for projective space, you get it for any projective variety by pullback. And so this leads to an important notion of dimension, which is different from the classical notion of dimension. As we just saw, you can, if you take a projective space, then it's homotopy equivalent to an affine variety of twice its dimension, and that's roughly speaking best possible. So you'll say that a variety has A1 dimension less than or equal to n if it's homotopy equivalent to some variety of dimension less than or equal to n. So from the point of view of the A1 homotopy category, I think the important point we want to make is that varieties are typically affine, or they're always equivalent to affine varieties. And this has a host of consequences. In the first talk this morning, we were talking about vector bundles on projective varieties, but in passing to affine varieties, we sort of turn off all extensions. And so you imagine that things that were before varying in families, where there were moduli problems, are going to end up becoming discrete. So in this homotopy category, we use these circles to build more complicated objects like spheres, and in particular, we define these homotopy sheaves. I'm not going to say too much about what they are, but they're basically defined by analogy with topology. You take homotopy classes of maps, but one important distinction is, number one, they're going to be sheaves, and they're sheaves in the Nisnevich topology. But just like in classical topology, they're sheaves of sets for I equals 0, just ordinary groups for I equals 1, and abelian groups if I is bigger than or equal to 2. And the reason we need to work with sheaves is that in topology, one of the classical theorems is that a weak equivalence between topological spaces is detected by homotopy groups. And in the algebraic geometric setting, isomorphisms in H of K, in other words, A1 weak equivalences, are detected by homotopy sheaves. So I made a point of describing two circles, S1 and GM, yet I only talked about a single index in my homotopy sheaves up there, so that corresponds to using just one of the circles. More generally, we have a bigraded collection of homotopy sheaves, which has been obscured by the Zoom chat. But the definition is exactly the same. That should be a GM. All right, so in 2006, Fabien Morel gave an ICM talk, and one of his key computations was to understand the first connectivity and homotopy of spheres. So in classical topology, you know, if you have an n sphere, then it's n-1 connected, and then you have the classical Brouwer degree, which tells you that the first non-vanishing homotopy group is the integers, and there's lots of tools for computing this. For example, you can, if you have a map from spheres, then you can use Sard's theorem to sort of take the preimage of a regular point and then compute the number of preimages and so on. So analogously, in Motivic homotopy theory, affine space with the origin removed is a sphere. It's not a sphere which is purely simplicial. In other words, it doesn't just involve those SIs. It also involves GMs. And one of Fabien's key computations is, first of all, to establish that this thing is connected in a way which is analogous to topology. So an minus the origin has the connectivity of an n minus 1 sphere. So the homotopy sheaves are 0 if I is less than n minus 1. And the n minus first homotopy sheaf is computed, and it's given by something which is an analog of the degree. It's given by this sheaf, which I'm not going to define, unfortunately, but the key feature here is that it varies depending on an integer n, which is some analog of a weight coming from, say, Hodge theory or something like that. So Milnor-Witt Kn is the analog of Z in Motivic homotopy theory, but it's Z that has some additional decorations. And so what's maybe one of the most striking things about the theory is that there's no sort of quadratic forms anywhere, but then all of a sudden when you impose A1 invariance, quadratic forms sort of appear from the void. And if you look at the homotopy classes of maps, the homotopy endomorphisms of one of these spheres, then somehow miraculously you get the Grothendieck-Witt group of stable isomorphism classes of symmetric bilinear forms. So I think this is one of the great kind of surprises of the theory. All right, so we really want to do topology, and one of the key tools we have in topology for studying lifting questions is the more Postnikov factorization of a map. So if you have any map, you can try to factor it into sort of simpler pieces. And so again, I don't want to get into details about what that factorization actually looks like, but if I have a morphism of suitably pointed connected spaces, then I can talk about the fiber of that map in a suitable homotopy theoretic sense. And at least if that fiber is connected, then I can factor the map into pieces which depend only on the homotopy of the fibers, and also the action of the fundamental group of the total space on the homotopy sheaves of the fibers. So these things are defined in exact analogy with the corresponding objects in classical topology. And so what does the more Postnikov factorization allow us to do? Well, suppose I have a map and I want to answer a question about lifting along a particular map. Well, it gives me an inductively defined series of cohomological obstructions to lifting. So now these cohomological obstructions are taking values in, well, sheaf cohomology groups, which are a priori very, very difficult to compute, but nevertheless, there is at least some sort of method to study these kinds of lifting problems. And the reason I mention this is because, well, we're going to rephrase the classical questions about stabilization of projective modules in terms of a suitable homotopical lifting problem. Now, in order to do that, we need to understand that projective modules actually have something to do with Motivic homotopy theory. And so we use the Grassmannian in order to do that. So you can build the an infinite Grassmannian, which is roughly speaking going to classify vector bundles together with some choice of generating sections. And here's where you see the real difference between Motivic homotopy theory and the classical setting. When we know that varieties are homotopy equivalent to affine varieties, on affine varieties, you typically have lots of generating sections, whereas on projective varieties, if you have a given vector bundle, it might not have any sections. So from the very beginning, there's a fundamental difference here. All right, so there's an object which is the infinite Grassmannian, which is defined in the usual way as an increasing union of finite dimensional Grassmannians. That's a well-defined object in the Motivic homotopy category, even though it's not a priori a smooth variety. On the other hand, there is sort of a classifying object, BGLN, and while these things are different as spaces in a suitable sense, there's an evident map from the Grassmannian to this classifying space, which classifies the tautological vector bundle. And roughly speaking, the fact that this is an isomorphism tells you, it says that in the Motivic homotopy category, well, up to homotopy, you can always choose generating sections, and any choice of generating sections, any two choices of generating sections are homotopy equivalent. All right. So the theorem that allows us to analyze vector bundles in this context was established by Morel with various hypotheses in place on K and N, and generalized by Marco Schlichting and then by myself, Mark Oiwa, and Matthias Wendt. And the answer is that the isomorphism classes of rank n vector bundles on a smooth affine variety are the same thing as A1 homotopy classes of maps from X to BGLN. All right, so this allows us to define something which is intermediate between vector bundles and, well, some other new object. So if I have a smooth variety, then it's always homotopy equivalent to an affine variety. So in particular, if I fix a Joannelou device of it, then I can look at the pullback map from vector bundles on X to vector bundles on the Joannelou device. And what I know is that vector bundles on the Joannelou device, by that theorem, are the same thing as homotopy classes of maps to the Grassmannian. And of course, X and X tilde are homotopy equivalent, so that's the same thing as maps from X to BGLN in the Motivic homotopy category as well. And so this set of homotopy classes of maps is going to be called the set of Motivic vector bundles of rank n, and we'll use this as sort of an intermediary in what we talk about later. So a Motivic vector bundle, therefore, is just a vector, an actual vector bundle or an isomorphism class thereof on some Joannelou device over X. Yeah, I guess now we have enough framework to go to applications. So as Aravind said, so we have a very general way to deal with this stabilization map. So first of all, we observe that the one that we defined at the very beginning is just induced by a morphism of spaces from BGLN to BGN plus R. And well, so as you can see on the board, so the map induced by this morphism of spaces is just the stabilization map we spoke in the beginning. Yeah, so now we can use somehow the technology we introduced. So for instance, if I want to study Xn1, so just adding a free factor of rank 1, I just have, in view of the Moore-Porsnikov tower, I just have to understand first the homotopy fiber and then some actions of a fundamental group. So in case R equal 1, then, well, we can very well compute the homotopy fiber. And actually, it's not quite a n plus 1 minus 0, but it's isomorphic to n plus 1 minus 0. And, well, so you see, if we have a map, if we have an actual vector bundle from X to BGN plus 1, so n plus 1 vector bundle on X, which is affine, then it corresponds to map G. And we want to say, okay, can we lift this map to BGLN? So in other words, can we just find a free factor of rank 1? So as Aravind said, so we have lots of abstractions in general. So say if X is of large dimension, then you will have lots of abstractions. But if we start with a scheme or a smooth affine variety, which is of small dimension, and here I mean the A1 dimension, then you see it's kind of easy to believe that if X is very small dimension, then there is no non-trivial map to a sphere of I dimension, right? So this is to the third theorem, which is saying that if X is of dimension D, A1 dimension D, then any rank R vector bundle, which R is strictly larger than D, it has a direct summand or free summand of rank 1. So this is the easiest situation, and if you look at the Moore-Porsnikov tower, then there is always a first subsection. So what happens when we are in the situation when there is this first subsection? Well, so there is a name. So this subsection has a name. It's the Euler class. It's well defined. Here we stated the theorem of Morel, which has a very, very long story. So actually, let me state the theorem of Morel first and then explain the story, because lots of people are involved in that thing. So the thing is that if X is of dimension D, then if you have a rank D vector bundle and you want to split it, then you have a single abstraction, and this single abstraction lives in a cohomology group, which is this HDX KD min of it. So remember that this KD min of it is the first non-trivial homotopy sheaf of the sphere, right? So this is the purely homotopical analog of the topological situation. And there is a kind of twist by det of E, which just takes into account the twist by the fundamental group of BGLN, which is just BGM. Yeah. So this is the theorem of Morel.
And actually, as I said, it has a very rich history. So first, if we take the field to be algebraically closed, and we forget about A1 dimension, and we just restrict to dimension, then we recover the theorem of Murty I stated in the beginning. But then, of course, there are many other fields. If you go to a general field, then previously there was a work of, Bhatwadekar and Sridharan, building on ideas of Norrie, who actually built a purely algebraic way of understanding this problem. And they could prove exactly the same, but also when X is singular, right? It just needs to be Noetherian, with maybe one extra assumption that Q should be inside. Anyway, so the two approaches are the same, but as I said, so it's a purely algebraic way of attacking the problem, but it might be slightly harder to compute. And also, there is a theorem of Schichting, who proved exactly the same theorem using mostly the same method as Morel, but without inverting the affine line. So Aravind said at the beginning that it was a controversy if we should invert the affine line or not. Anyway, we get the same results, so the controversy is solved. That's it.
So I hope it's clear that the world is sort of separated into several domains after Morel's theorem. There's the case of negative co-rank, which is some stable situation and is roughly k-theoretic in nature. There was the situation of co-rank 0, where we had the theory of the Euler class and also Suslin's cancellation theorem. And then there's the situation of what happens in positive co-rank. And the positive co-rank situation is really unstable. And so one should expect that the answers one gets are going to be comparatively more complicated. But we have at least a systematic approach to doing this. Namely, if we study the homotopy sheaves of affine spaces minus the origin, then we can hope to get some obstructions, if we can actually write down what these sheaves are, and maybe those obstructions are actually computable. And so that's what actually happens. So if you're familiar with homotopy groups of spheres, you also know that there's a range, a stability range, and the homotopy groups stabilize after some range. And below that range, they can exhibit all kinds of strange behavior. The situation in algebraic geometry is very, very similar. There is some sort of stable range, but remember, there were two circles, and so stabilization is a slightly more complicated notion. So Morel actually made some conjecture about the first stable homotopy group of sheaves, and that conjecture looked similar to this one right here, but that conjecture was verified by Rondig, Spitzweck, and Ostvar, and based on some geometric computations that we did, we made a conjecture about what the unstable homotopy sheaves of spheres were. And it turns out, number one, that if you know this conjecture, then Murty's theorem essentially, then you could understand sort of splitting of co-rank 1 bundles just based on what we know about cohomology of these sheaves. But maybe just to give you a flavor of what this computation tells you, the form of the computation is inspired by topology as well. And so maybe this is the new sort of feature that A1 homotopy theory gives you. It gives you some kind of way to decompose these unstable homotopy sheaves into things that look familiar from a topological standpoint. So this GWNN+1 is once again a reappearance of something quadratic. It's some kind of Hermitian K-theory. And the map here is stably the unit map from the sphere spectrum to the Hermitian K-theory spectrum. So there's some piece that comes just from Hermitian K-theory. Again, in topology, something similar is known. If you look at KO theory for vector bundles, it detects the first two homotopy groups of the classical sphere. And then the fiber also has some sort of purely topological interpretation. It's something that comes from a suitable Hopf map. So each of the pieces here means something, even if you don't understand precisely what these objects are. So anyway, we conjectured that there was this stable form, and in fact, there is an unstable version of this as well, that it becomes slightly more complicated, and then the numbers change a little bit, reflecting unstable phenomenon. And so recently, in joint work with Tom Bachmann and Mike Hopkins, we established this theorem, basically by establishing an analog of the Freudenthal suspension theorem in Motivic homotopy theory. And as a consequence of that, we can just get a splitting theorem for co-rank 1 modules, extending work that John and I did in dimension 3 and 4. And basically, once we know this form of the computation, we sort of worked out exactly what the cohomological obstructions are. So the upshot here is that, in fact, these homotopy sheaves are computable. And we can actually understand what the output is. These aren't just some abstractly defined sheaves of groups and computing some sheaf cohomology. And the assumption that K is algebraically closed appears there in conjunction with affineness, because there is going to be a secondary obstruction beyond the vanishing of the Euler class. And in this case, those two conditions combine to tell you that the secondary obstruction is automatically trivial.
Yeah, so we can use these techniques to prove the splitting results, so in co-rank 1, but we can also use it to actually prove the full Suslin question. So, namely, we want to know if we have two rank d-1 vector bundles, so if they become equal when you stabilize, then are they actually equal from the beginning? And well, if you use this thing, well, first of all, it's slightly different in nature, because you have to understand splittings, you have to compute abstractions. And if you want to deal with injectivity or just proving that it has trivial fibers, you have to enumerate vector bundles, right? But this Postnikov tower allows you to do it in also a very systematic way. And as I already said before, so what we know from the homotopy sheaf before is enough to compute and to compute the cohomology at the right spot. So in that case, just saying that there is no abstraction to being injective. So this is a work which was inspired by work of my students, Tariq, Syed, and Pengdu. And well, let me say that it's not the end of the story. You could say, okay, I want to understand rank 2 bundles on 4 folds, and you can run exactly the same kind of abstractions. So this is as far as we can get. So there's no precise result in that talk, but you can say something also about rank 2 bundles on 4 folds. Okay, but now, as we are reminded every time we give a talk, most varieties are not affine. So can we go back to a more general situation? So now we want to, in the rest of the talk, we want to actually study a little bit what happens in say, projective or quasi-projective situation. So we have this weird notion of a Motivic vector bundle, which is kind of abstract, right? So it's a set of maps in a weird category. So the idea, we know, so Aravind told you that it's equivalent to describe vector bundles on some Johanneau device of X. But can we really understand the nature of those bundles? So first, mathematicians know if we want to understand something, we start with the easiest case, and the easiest case is just n equal 1. So in that case, it's kind of easy because, so rank 1 bundles are just, line bundles. And those line bundles are exactly the same if you are over X or over a Johanneau device. There is no difference. So in that case, a Motivic vector bundle of rank 1 is just a line bundle. So there is no difference. But if you start the next case, so n equal to 2 already, it's different. So if we want to explain the difference, so maybe there is a nice way to do it, is just to say, okay, let's specialize to a field which is well known, like the complex numbers. And let's try to give a flavor of what Motivic vector bundles are. So in case K is equal to C, then the good thing is that there is a complexorization. So from this weird homotopy category to the usual homotopy category of topological spaces or nice CW complexes, which is not quite mysterious, because if you take a smooth scheme, then you just consider its complex points. S1 is even easier to understand. S1 is S1. And the homotopy sheaves we introduced previously are just sent to the homotopy sheaves, or the homotopy groups, sorry, of the complex points of C. So it's a nice way to check if what we are doing is just completely out of bounds or not. And so the last thing for vector bundle is that if you want to complex realize this BGLN, well, you get the usual classifying space of unity bundles of rank n. So as a result, you get a string of maps. So you have your Motivic vector bundles on the left, and then you complex realize, and you get the set of topological vector bundles of rank n. There should be an n, so there's no miracle. You don't get other ranks than n. So, so you see from a Motivic vector bundle, you get a complex topological vector bundle on X, right? So if we look at everything, on the left, we have the set of actual algebraic vector bundles on X. Then in the middle, you have your Motivic vector bundles, and on the right, you have your topological vector bundles. So I think this picture explains very well what is the nature of these Motivic vector bundles. They just sit in between, right? So it's either way. So it's either a topological version of algebraic vector bundles or an algebraic version of topological vector bundles, depending on the map you look at. So now there's another questions. Again, can we understand the image and fibers of those maps, right? So, well, so first, I think it was your turn. No? I'm not sure. Anyway, so I can say something. So, yeah, so we first focus on the right map. So from Motivic vector bundles to actual vector bundles. And, well, we note first that there is it's the same way to construct elements on the left or on the right. So on the left, you use this Motivic Moore-Postnikov tower, and on the right, you use the actual topological Moore-Postnikov tower. And the good thing is that this complex realization sends one to the other. So you could say, okay, whatever I'm able to construct on the left should be also constructible on the right. But of course, you have some kind of algebraicity assumptions to make, right? So if you look at the case of complex surfaces, then we know that the topological vector bundles on XC are just classified by their first and second Chern classes, right? And well, in fact, if they are algebraic, then you can construct an actual vector bundle on X, which has the same Chern classes. Well, the Chern classes on the left, which are the algebraic ones, are sent to the topologic one on the right. So in that case, if you take n equal to X is a surface, then you see that you have a very precise answer on the image of this map. It's just, well, some kind of algebraicity of Chern classes. You can try to run the same thing. So if you go to threefolds, then you want to say classify rank 3 bundles, then you do exactly the same. If you work on the left, then you actually use your Moore-Postnikov tower, and you see that rank 3 bundles, Motivic rank 3 bundles, are just classified by 3 Chern classes, C1, C2, and T3, subject to a condition linking C1, C2, and T3. And it's exactly the same condition on the right. So again, you have a very complete way of understanding the image of this map. And well, you can try to do the same for rank 2 bundles. It's slightly more complicated, but still, you get exactly the same picture. Okay, sure. So it's my turn to state the bold conjecture. So I was hoping that you would do it. Okay, so now we can, since we know how to build vector bundles on the left and on the right, and we know that roughly the invariants are the same, they are discrete, as Aravind said, so there is no moduli space of vector bundles. One can say that if the variety is simple enough, then the invariants are the same on the left and on the right. And well, so the whole conjecture is to say what is simple enough, right? So simple enough could be something like a point, that's simple, but maybe something more interesting is a cellular variety. And whatever that means, well, that means, for instance, that projective spaces are cellular, right? So you should be able to build your thing like using spheres, so Si, SMAS, GMJ, and well, this should be some kind of co-limit and so on and so on. But so there is a precise notion of cellular variety. And well, so we conjectured that this is actually, well, first surjective, and then if we are very optimistic, bijective. So whenever there is a conjecture, we should test it in simple cases. So we did for P3. For P3, it's very easy. So the map is actually a bijection. For P4 and P5, we know that it's onto again. So what is the technique? We run this Moore-Postnikov tower, we get obstructions, and we say, okay, so this is in some sense algebraic because we have the same obstruction on the left. But if you want to prove that it's actually bijective, it's more difficult because you have to compute Homotopy sheaves, which are hard to compute, right? But anyway, so those are evidence that it could be positive, the answer to this conjecture.
So we wanted to give some evidence beyond these sort of low-dimensional cases, and there are many, many open questions about algebraizability of vector bundles on projective space. For example, I think it's unknown whether there exists a single vector bundle, topological vector bundle in projective space that doesn't admit an algebraic structure. And that previous conjecture sort of is trying to say something about exactly that kind of question. And so one of the initial methods of potentially constructing a counterexample to that was a construction of Riesz. And so there's a fun history around Riesz's construction as well. But basically, Riesz built some topological vector bundles. Elmer Riesz built topological vector bundles on Pn for large values of n, which had trivial Chern classes, but which were non-trivial. And so let me just sketch the ingredients of his construction. Basically, because there's, if you take the 2p minus 1 sphere, or Pn for any n, and you collapse Pn minus 1 inside it, then the cofiber of that is a sphere of a suitable sense. In topology, it's just an even-dimensional sphere of S2n. And so there's a Motivic analog of that kind of construction. And likewise, so therefore, if you'd like to build vector bundles on P2p minus 1, then it might suffice to build homotopy classes of maps from some suitable sphere. So this is exactly what Riesz did. He took P and odd prime, and it's a classical result of Serre that the 4p minus third homotopy group of S3 is Z mod P, the P primary component of it. And by adjunction, that 4p minus third homotopy group of S3 is the 4p minus second homotopy group of BSU2. And so that corresponds to a rank 2 bundle on a 4p minus 2 sphere. And if you can lift it along the collapse map, then you get a vector bundle, a topological vector bundle of rank 2. And so Riesz proved that it actually does lift along the collapse map, and you do indeed get a non-trivial topological vector bundle on P2p minus 1 for any prime P. So one of the things that we proved is that, and generalizing what Jean said, well, we have some sort of topological construction, and if you can lift all of those topological constructions to algebraic geometry, then you can construct an algebraic vector bundle, but now on a suitable Johannelet device. So in this case, a Motivic vector bundle. And so that's literally what we did. We sort of constructed lifts of all of these ingredients and then proved that the Riesz bundles actually lift to a Motivic vector bundle. And so this is some evidence of that Motivic vector bundles do see all topologic vector bundles. These are sort of strange vector bundles in some sense. And this is just an example. There's sort of many other things that are like this that also can be lifted in this construction. So this is another way in which Motivic homotopy theory sheds some light on some sort of topological question.
Yeah, and it's again my turn to state the conjectures. So we dealt with Motivic vector bundles, and but we are very much also interested in actual vector bundles. So we could ask, what is the difference between Motivic ones and usual ones? So Aravind told you that obviously there are many more actual vector bundles than just vector bundles, right? Because he told you all extensions are just identified on top. And besides, all vector bundles are generated by global sections. So there is a huge difference between the two sets. But can we still say that, okay, so the guy on the left is huge, the guy on the right is discrete. So we could say, okay, maybe it's surjective. So any Motivic vector bundle actually lifts to an actual vector bundle on X. This is a question that was posed in collaboration with Mike Hopkins, also the previous conjecture, I should have said. And again, you start with trying to understand very basic cases. So if X is a smooth curve, then it's very easy to prove that it's actually true. If you go to surfaces, then it becomes a little bit more complicated. But I told you before that well, roughly the guys on the right are just classified by Chant classes. So yeah, I stopped there. But just to say that if we have two Chant classes, we can build the rank 2 bundles, and that's a proof that it's surjective in that case. But in general, it's wide open. Maybe it's a good time to thank you all for your attention and your virtual attention if you're not here.